All right, welcome back to FROBOTs 101. I am your host, Jerry Chan, and today we're going to continue on our last exercise, and which was getting our little robot Optimus Prime to drive in a straight line. So, remember, just a quick recap, we talked about the coordinate system in FROBOTs, how the degrees are defined, and how you actually get the XY locations so that you can sort of figure out where you are in the game grid. So today, what we're going to do is we're going to go over counting and time. Now, counting and time is important because we want to be able to trigger behavior in our robot, which depends on how long it's been doing something. So remember, because we don't actually have access to a traditional for loop, when we're programming robots, we kind of need to just know, like, we should do something for X period of time, and then when that's done, when our countdown has gone to 0, then we need to change state, right? And so we'll illustrate this in the example of getting little Optimus Prime to stop moving north, because remember, we had him just continually drive north until he just crashed his little head into the wall enough times that he exploded. Well, poor little Optimus we're going to need to save him. So what we're going to do is we're going to play with counters. So let's jump over to our code, and let's get cracking. So first thing we want to do is we want to store something like a count. So where would we put this? Well, turns out that we can create variables however we want, because this is just a Lua function. But it turns out that if we want this variable to persist across execution cycles, namely, if we're going to store the count and we're going to subtract something from the count every time we're executed, then we kind of need to know what the previous count was. So instead of just declaring a local variable in this function, which of course would just get lost every cycle because it doesn't have any persistence, we're going to stick it into our state variable. And this is why I said that the state variable is kind of like the catch-all bucket of anything that you want to remember, any sort of message that you need to pass to yourself. So in this case, the message is a count. So what do we want to do? First, we want to instantiate the count to something meaningful. So let's once again go into our nil, or our start state. Our start state, as well as moving ourselves to the drive north state, will also set this count variable. And notice I'm using count without the underbar, because the underbar is like the field names which have some special meaning outside for the virtual machine. But count is just something that we're defining ourselves, so we don't need to put the underbar. We can just name whatever thing we want. So count seems appropriate, and let's set it to something like, I don't know, 20. Okay, so 20 cycles, it's going to, do something. Now, every time we drive north, if you're driving north, what we want to do now is obviously to decrement that count. So what we do is we set the count equal to itself minus 1, tried and true traditional way of decrementing a count, and that's it. So what we could do is we can now add this also to our display so that we can sort of know ourselves what's going on here. Let's call it C. So C is my state.count, not cannot count. And there we go. So save that. Let's jump to our code and see what happens. There you go. Now you can see Optimus Prime is moving up, and you see the count quickly decremented. Oops. Ooh, it went past 0. And it's just continuing to decrement. And poor Optimus is not stopping, and he's making a beeline for the wall, and he's gonna kill himself again. Well, what happened there? Well, computer science happened. Bugs happened. So let's see what we did wrong. If we go back to our code, we were guilty of decrementing the count, but not actually doing anything when the count hit 0, right? So clearly we need some transition function to move us from driving north state to something else. So that something else state is, let's just call this new state stopped. Okay. So what we're going to do here is that if we are, right now it's checking if we are in the driving north state, then continue driving north and decrement. But what we really want is we want it to also check whether or not it's time for us to move out of the state. So what we should do is not only do we check whether or not we're in the drive north state, we should also check and state.count is greater than 0, right? That means that we're only going to do this when it's greater than 0. Now, if it's not greater than 0, namely we've actually hit this condition where we want to change state, then we can put that as another else if. So we can, or else, sorry, else state status equals stopped. And before we make the same error, actually stop. We set it to drive 0. First 0 doesn't really matter that much since it's a degree. It doesn't really matter which degree you're pointing in as long as you go at speed or throttle 0, which means you're going to stop. So once you've stopped, that should really stop everything, and Optimus is not going to do anything else. So let's give that a try and see what happens. Okay, he's moving up, and he's hit 0, and now he stopped. Excellent. Success. Always good to have a program do what we want it to do. All right, so mission accomplished. So now that we have Optimus doing something on a count, the other way, it's worth mentioning the other way you could do this. You could actually just make a Lua call, which would get the system time. And then from that system time, just keep checking whether or not the elapsed time has gone by. So for instance, if you wanted to drive in a certain direction and basically stop only when 1 minute has elapsed, then what you could do is get the system time from Lua, and just every time you do your state transitions, check whether or not the time that you want to make that transition has been elapsed, and then just make your state transition that way. I kind of find that it's easier to do counts because the one thing about system time is you can never be sure how much real time goes by. So for instance, if there's a lot of things going on in the processor, it might actually take longer to do the same thing that, the same distance that you wanted to drive sometimes rather than other times, in which case you're not going to have a consistent amount of driving happening. You end up driving, say, less if the CPU was more busy. So that's actually the reason why it's not really that recommended, but I can imagine there'd be some interesting strategies that people might come up where using system time may make more sense than using a count decrementer. Anyhow, so let's move on to our final exercise for this class. We want now for our little FROBOT to drive in a little bit more complicated pattern, right? We want him to do something more than just go somewhere, stop. What we want to do is we want him to drive in a square pattern. So let's quickly go over how we might do this. I find it's very much useful. Very useful to go over the algorithm on paper before we actually go off and write it. So what we actually want is, if our friend Optimus here we want him to say drive in this direction. We don't want him to crash into the wall. So let's do something more intelligent this time. Let's say that he will stop within 50 meters of the boundary wall. Okay? So wherever he starts, because we don't know where he starts, that's random. But he's going to stop within 50 meters of the boundary wall. And then at that point, he will have a state transition. Let's call this transition 1. And he will start moving south in which case at that point, same thing, within 50 meters of the boundary wall, he will have a second state transition, and he will move to traveling west. Similarly at this point, right, 50 meters, we don't want him to crash his little head, and then the third state transition, and then he would go north again, at which point he will stop when he is also within 50 meters of the north wall. Okay, so how are we going to do that? So this state transition number 4, and now I'm labeling all these transitions so that we can identify them here. Okay, so what we actually want to do, I find it always useful to just list out the states. So he's going to start in a state that he will immediately jump into driving east, right? Drive east. And then he's going to change to drive south, and then drive west, and then drive north, and finally stop. The terminal condition stopped. All right, what are we missing? Well, we're missing what is going to trigger these state transitions. Okay, so let's think about it. We want him to stop when he's within 50 meters of the boundary wall. What do we know about this point at state transition 1? Let's label this. This is state transition 1, state transition 2, state transition 3, state transition 4. At state transition 1, we know that the x coordinate must be 50 meters from the boundary. Well, we know that the arena is 1,000 by 1,000. And if you didn't know that already, well, now you do. For this particular arena, the boundaries are 1,000, 1,000. So within 50 meters means the x-coordinate is less than 950. So if x is less than 950, then you want to transition, right? Similarly, when you're moving south, what is the coordinate you need to be checking here? You need to be checking y. So what is it? What is the coordinate here? You know that y is less than greater than 950. Yes, I had it off by one logical error here. I meant greater than 950. Greater than 950. Good on you for those of you who caught me on that. And when we're doing state transition 3, you're moving this way. Remember, this point is a 0x and 1000y. So what we're checking for is that if x is less than 50. And then finally at this point 4, we know that this point up here is 0, 0, right? So what we want to do is we want to check that y is less than 50. Oops. So that should get us what we want here. So we've actually just mapped out the algorithm right there. So now we just have to translate this algorithm to code. So let's do that. All right. So through the miracle of time-lapse photography, I have typed out that algorithm. As you can see here, you can see that we start with the initial state. We will start driving east. And then we have our Uber if statement clause here, our state transition table. If we're driving east, then start driving in easterly direction. Notably, 0 is east, remember? Now, if the location of your x coordinate, if your x coordinate gets above 950, then we want to transition to the driving south state. And we do that simply by setting the status, as we've always have. And then that's it. And then similarly, all the other state transitions. Once you're in south driving state, drive south, check the condition that will move you from this state to the next one, which will be driving west, etc., etc., etc. And then finally, if you are stopped, if you've been transitioned to the stop state, which is what you were doing last when you were driving north, checking that your Y location is less than 50, you become stopped, and then when you've become stopped, you stop. There you go, and that should do it. It's doesn't look so bad when you just type it out. So let's give it a try here. Great, look at Optimus go. You can see he's moving. He's driving east. You can see his X and Y coordinates there in the debug display. Very useful to always leave messages to yourself in debug. You can see our count is nil because we got rid of that variable. We didn't need our count variable anymore. Now let's see if he stops before he needs to, before he crashes. Oh, and he stopped. Yes. All right. Hopefully he starts moving south. There we go. We see him driving south. We notice the status has moved to driving south. And there you go. Meanwhile, the random FROBOT is moving around in a random fashion, throwing cannonballs everywhere. It's nothing to worry about. It's very low chance probability that he'll actually hit our FROBOT. Not zero though, but there we go. And now he should be driving west. And now that he's driving west, the next time the execution cycle goes, he does the drive command. And he's going there. Oh, while our FROBOT's moving, it might be worthwhile mentioning the grids. The grid pattern on the game grid actually has a meaning. For those who really want to get into the strategy here, every little square is a 10 by 10 meter location. So you can sort of work out how fast your FROBOT is going by how many squares he passes in a given period of time. Now, the FROBOT itself, the representation of the tank itself is a 2 meter radius circle. So if something coincides with your 2 meter radius circle, then there's a collision. And so you can collide into other FROBOTs and other and damage each other. So that's something you probably generally want to avoid. And let's see if he stops. And if he stops and goes into the stop state, and we're done. Excellent. So there you have it. We have successfully created a FROBOT that has complex movement, that basically can drive in a straight line and then drive in a square pattern, stopping on given conditions that we have outlined. And we are well on our way to designing the next stage of our FROBOT design, which is scanning and shooting. So tune in next time when we go into how to use the scanner and the cannon for the FROBOT. Thanks for joining us, and we'll see you next time.